have much to say from the organizational point of view. I think we started off reasonably well yesterday. Let's see what we get to today. Two little things. Lars still wants people to tell him if they're planning on coming to the buffet on Friday. That's right? Correct?
Yes.
Good. Ideally, if we could do that today, I think that would be good. Is that right?
Right.
Yes? Very good. The other thing is Danny suggested, and I think it's a good idea, that at some point at the end of the day, we could just have a little informal gathering if people want to, for a chat, just to debrief as to what we've been thinking about when we had the time to disappear for a bit. So I suggest something like 4 o'clock in the afternoon, people that want to just come in the little room in the back there and have a coffee. It's not a sort of meeting, just to talk about whatever. And we can do that every day. Might make sense. After that, I have nothing really to say, apart from the fact that I think we've not thought through in enough detail how we're going to moderate the different sessions. And so my suggestion is that the main speaker, so the person that gives the long presentation, essentially acts as moderator of that session. They can moderate himself. And I suggest if there is need for assistance, maybe the speaker from the previous day could, help out. If it's just to move things around, and basically because I don't want to interfere too much all the time myself, it doesn't make any sense to get a bit of rotation. I think we don't have a problem getting people talking really, so it shouldn't really be hard. And the plan then is to have a long talk, which is about 15 minutes, whatever it is. And then today we've got 2 shorter ones. It's on the pasta and on the transition to the top layers. So I think that will cover all the transitions more or less. That's the plan for today. So, Jack.
So thanks. As go along, please object, ask questions, complain. I'm the moderator, so I'll just cut you off. Let's see, astro-material science. I'm not really sure whether that's a field of science or not. In the event it is, we may have it pretty much to ourselves. I want to talk about a bunch of neutron star cross properties, and for this talk I'll use molecular dynamics. So this is a very classical talk. We've got a lot of superfluid things to be discussed, but not today, or not during my talk. Some of the things we look at, thermal conductivity and cross-cooling, viscosity, damping of oscillation modes. I'll talk about the shear modulus a little bit, and then we'll have more discussion about possible oscillation frequencies for shear oscillations of the crust. And I also want to talk about the strength or the breaking strength of the crust, and a little bit on star quakes. So a whole bunch of properties are important for the electromagnetic neutrino and gravitational wave radiations of neutron stars. Okay, so you should have in your mind the beautiful Danny Page picture of the layers of neutron star. Starting with the thin atmosphere, I'm not going to talk about it. We'll get to that towards the end of this conference. The envelope, a low-density region where there's a big temperature gradient, it's important for the relation between the surface temperature and the interior temperature. I presume Danny is going to talk a little bit more about that. We have an accreting neutron star. It can be warm. Material falls into a liquid ocean. So there's this liquid region at the surface. By the time the density has gone up to about 10 to the 10th grams per cubic centimeter, the high density leads to the freezing. So this is where we're forming the crust. So you form new crust when the liquid in the bottom of the ocean starts to freeze. That's the outer crust, so you've got neutron-rich ions and electrons. There's a high electron Fermi energy, so the electron capture drives the ions more and more neutron-rich. By the time your density is a few 10 to the 11 grams per cubic centimeter, then you also have some free neutrons, and so that's the inner crust. And then finally, at the bottom of the inner crust is where we believe pasta lives. So these are the complex shapes. So the crust is formed when the ocean freezes, and then the crust melts with the pasta phases to form the uniform liquid of the core. Okay, got a very big electron Fermi energy. And so that's a great simplification. The electronic structure of the neutron star crust is very simple. So a lot of the complicated chemistry is greatly simplified in a neutron star just because the electron Fermi energy is so big. So the ions are completely pressure ionized by the high electron Fermi energy. So we don't need to follow the electrons explicitly. They are slightly polarizable. So you have an ion that's surrounded by its screening cloud, slightly polarizing the electron gas. And if you have two such ions, then there's a Coulomb interaction between the ions, 1 over r, but then the screening clouds also interact. And so you've got essentially a Yukawa interaction where the screening length, lambda, depends on the electron density. So for much of my talk, the only place the electrons enter is in the screening length. And then we'll be following essentially the classical ions interacting via these Yukawa interactions. One thing to keep track of is the composition of the material. So we ask our nuclear physics colleagues to tell us what nuclear reactions go on, what different kinds of ions you produce. The composition of an accreted crust is expected to be different from that of a cold catalyzed crust. And one parameter just to keep track of the composition, so-called impurity parameter Q, which is just the dispersion in atomic number Z, the charges on the different ions. So if you had a single species, then Q would be 0. If you've got some dispersion, a whole bunch of different species, different Z's, then you can have a big impurity parameter Q. I just wanted to keep track of a few questions, because you guys are being too quiet. Anyway, go on. So I'll say this impurity parameter dispersion in Z. How big is it? How does it change with density? Different nuclear reactions can tend to burn away the impurities. How does the impurity parameter for an accreted crust differ from that of a cold catalyst?
So I'll start it off. Could you repeat again the large electron Fermi energy does something to the ions? You said
Oh, okay. So yeah, if you have atoms, you just basically they're under very high pressure, and the high pressure ionizes the atoms. So the electrons are unbound. They now go into this Fermi sea between the ions.
Okay.
And the electrons are not localized on each ion because of their very high Fermi energy. So it's difficult to localize the electrons. Okay, so there's a Coulomb lattice in general of ions. They can have different charges. And one question you could ask, do you form a regular crystal or an amorphous solid? So let me just give you a little picture. These are just some very small 3,000 ion simulations. Regular crystal is regular. This is actually near the melting point, so there's a lot of thermal fluctuations. But you see the ions oscillating around their lattice sites, and you have regular lattice planes. So that's a crystal. That's what you expect. An amorphous solid basically looks like a liquid. The ions are much more randomly distributed. This, in fact, is a solid. If you like, it's sort of a frozen liquid. It has a shear modulus. In fact, the shear modulus of this is remarkably similar to that, which is maybe a little counterintuitive, but true. However, transport properties, the thermal conductivity, the electrical conductivity of a crystal lattice is much higher than that of an amorphous solid. So electrons trying to go through this amorphous solid scatter a lot more from the ions. And so the question is the crust a regular crystal, or is it amorphous?
Chuck,
Uh-huh.
on the right figure, why each ion is like a little cluster of little balls? What's that?
You are actually looking at several planes.
Out of the projection.
Yeah, so there are random distributions, and so you get, there's a Gaussian distribution of ions about the lattice sites. Okay, why might you form an amorphous solid? There's two arguments. One is if you quench the system. If you cool it really quickly, you can, in the laboratory, you can make glasses that way. Alternatively, it was thought that if you had a lot of impurities, the impurities will interfere with making a regular lattice. And it was thought that if you had a lot of impurities, that could give you an amorphous solid rather than a crystal. But our explicit molecular dynamics simulations disagree with that. Okay, wanted to talk about the composition. So which ions are making up the crust? So you're dumping material, hydrogen and helium, onto a neutron star. You've got some hydrogen there, so there are some bunch of free protons. Those free protons can capture on nuclei which are already present, leading to the rapid proton capture nucleosynthesis on an accreting neutron star. Okay, so this is periodic table. So atomic number of protons is up this way, number of neutrons is out that way. You're capturing a bunch of protons, so you make the nuclei proton rich. And these little gray squares are the stable nuclei. So this is on the very non-neutron star side of the periodic table. So this is the proton-rich side of the value of stability. And basically you capture protons, you keep capturing protons, till if you captured one more it falls off. So you have to wait for a beta decay. And then you capture some more and you can, the material flows to higher atomic mass that way. And so, for example, this is a Michigan State simulation, Schatz et al., of a X-ray burst. They predict the rapid proton capture ash. So the endpoint, the composition that's left over when the nucleosynthesis stops. For example, if you run out of hydrogen, then you stop capturing protons. The material cools off, and you have some composition. This composition then gets buried. Further accretion takes it to higher density. As it goes to higher density, the electron Fermi energy rises and you have electron captures. So electron capture starts making it more and more neutron rich. So you're going to essentially go diagonally to the lower right, and you're going to march all the way across the periodic table. And so this is one simulation of electron capture by Gupta et al. And a density of 10 to the 11 grams per cubic centimeter near the bottom of the outer crust. Here was the composition. So half the material has a Z of 34. Actually, I should say 32 selenium. And the other half of the material is a range of lower Z, all the way down to oxygen. Although this is a very neutron-rich. It's oxygen-24, very neutron-rich isotope of oxygen. So we have this composition, and we're going to build new crust out of it. So this is a little movie from Michigan State of the electron capture. So this rapid proton capture nucleosynthesis started down here, moved all the way up to around, this is mass number 100, and left a range. So most of the material is up here, but you have a range of lighter nuclei left over. The stable ones are these black squares. So you're on the proton-rich side. And then we're just going to bury the material. As you bury it, it undergoes electron capture, and it marches along. Its density is increasing, and finally we reach a density 10 to the 11 grams per cubic centimeter near neutron drip, and most of the material is now approaching the neutron drip line. You have, so most of the material is up here. Eventually it's going to wind up at selenium Z of 32. Well, why don't we say Z of 34? That's better. And you've got a little bit of oxygen left over and so on. So that's an example of a distribution of composition in the near the base of the outer crust. So one question you can ask the nuclear physicist is, when you have an X-ray burst or nucleosynthesis taking place on a accreting neutron star, how clean does the material burn? Does it all burn to a single chemical element, or is there a distribution of unburned lighter material also left in the ash?
Sorry, Kat. So, how is there any idea how sensitive the final result is at the inner crust transition? How sensitive it is to whatever, how clean the system is, as you said, at the top. When you finish the burning and then start the burial, how sensitive is the final?
Yeah, it is sensitive. I mean, it depends on how it burns.
Okay.
If you have the superburst, which is you're burning a lot of carbon, you get a very different ash than this rapid proton capture nucleosynthesis. And it can also depend on the conditions. If they're not as extreme, you don't burn all the way to mass number 100, you get lighter. So different simulations will give you different compositions. And that's certainly something one should explore more. Okay, want to take that complicated composition and freeze it. And I guess these figures are really hard to see. This one's a little clearer. This is a molecular dynamic simulation. There's 27,000 ions in a box. There's this complicated composition that I showed you. So half of it is this high Z material, and the rest is this range of Z's. And we've carefully adjusted the temperature during the simulation. So about half the material is a liquid. So this part down here is a liquid phase. There are periodic boundary conditions, so the liquid actually extends a little bit up to the top there. And then you see that you've got a solid here. So those are the lattice planes. So even though you have all this complicated junk and impurities, it forms a nice regular crystal. There's very nice lattice planes. So the solid is not amorphous. just has a bunch of impurities in it. You start with a mixture where the impurities are uniformly distributed between the solid and liquid, and just let it run for a while, and you find chemical separation. Here's the ratio of the composition in the solid to that in the liquid. The low-Z material like oxygen, that ratio can be 10%. So the liquid is enhanced in the low-Z materials by a factor of 10 compared to the solid. So I don't know if you can see this. Here are where the oxygen ions are. There's few oxygen in the solid up here. All the oxygen likes to go down in the liquid. So you get this chemical separation in the material freezes.
What's the density where this is simulated?
Okay, the freezing actually takes place at a density of around 10 to the 10 grams per cubic centimeter.
Simulation depends on what the density and the...
So it's actually, it just depends on the Coulomb parameter, which is, if you like, it's some ratio of density to temperature. But typically on an accreting neutron star, the star's a little warmer, so it freezes around 10 to the 10. So the outer crust is only a region between 10 to the 10 and few 10 to the 11 in density. Okay. Making new crust here, want to look at some properties of the crust, and in particular, want to look at the thermal conductivity, how the crust cools. So here's an example, and I guess Danny, I assume, is going to talk more. Neutron star accretes for a long time, and so all this accretion heats up the crust. Then at some point the accretion stops, and Chandra images the star at this point. You see that the star is hot, and then you just look at it later and watch the star cool. So it's surface temperature versus time. The time time t equals 0 is when the accretion is observed to stop. And the star cools relatively quickly. I guess I should yell at the theorist. Theorists took the nice experimental error bars and arbitrarily doubled them and called them 2 sigma error bars. Don't do that. If the experimentalists plot 1 sigma error bars, just plot what they, anyway.
Is this assuming spherically symmetric accretion?
I'm sorry?
Do these calculations assume that the accretion is over the whole surface of the star and spherically symmetric?
They assume basically that the star was uniform to begin with,
Okay.
and then the accretion stopped, and they're just letting it cool.
Is that reasonable if you have accretion around an equatorial belt?
That is a big can of worms.
I would assume that the matter then will flow toward the pole. No?
Yes.
At the surface it makes a difference, but when you look at density much higher,
Even if you have a boundary layer of some kind, it shouldn't give you a massive temperature
I mean,
gradient.
you cannot make a mountain on the equator, so the matter should flow toward the
But
pole.
you can't make it hotter even if you didn't have matter piling up.
Excuse me?
You couldn't just make a hotter belt. I mean, without making a mountain, you couldn't just make it hotter. I mean, would that make a
But
difference
I
to
don't
the
think
burden?
that would have an effect deeper, because the temperature is much higher inside than the surface.
Before you go on, may I ask, just, this may be silly, but these red lines here, they correspond to the black lines in the previous slide, is that correct? Because I'm just curious, it looks like that data there is there's a lot more variation there than implied in the red. You know, it looks like it goes up and down quite a bit in the count rate here from the RxCE data.
Oh, RxCE is not particularly sensitive. The astronomers should look them. This
Is that back
That's basically background. That's noise. That's not.
Ah, that's just.
This is all consistent with 0.
Right, oh, okay.
I mean, it goes negative, so that's just something we
That's
don't
really
know about
cool.
1731.
Ah, okay, so that's why it doesn't resolve. Thank you.
This dot has the RxT data.
That's right. This is the all-sky monitor of RxD.
Yeah, that's not,
And on top of this, you have the Chandra.
yeah,
Which are
Yeah,
not
so
thank you.
you obviously need to look with a more sensitive telescope image. Okay, what I wanted to say is all the black curves here assumed a crystalline crust, and this one curve up here assumed an amorphous. And so it's quite striking. There's an incredible sensitivity. An amorphous crust just has a completely different, a much longer cooling timescale than the data does. So the data really strongly favors a crystalline crust, and actually favors a crystalline crust with relatively few impurities.
Chuck,
Uh-huh.
I think they did have the thermal conductivity from the superfluid phonons.
Okay,
It's only electrical conductivity, from
That's
electrons now.
that's
So
correct.
maybe you can have a nuclear crust,
Um,
but phonon, superfluid phonon will transport the heat.
I mean, it's certainly an interesting thing to add. My gut feeling is it's not going to be enough.
The outer crust.
Oh,
No, this will be sensitive.
that's right.
Oh,
It's
it's
actually,
Five.
most of the sensitivity is actually in the inner crust here.
Okay.
So this is the thermal conduct. You're most sensitive to thermal conductivity of the inner crust at this point. So it's an interesting question, but my feeling is that amorphous is just so low, the thermal conductivity. But I mean, you should do the calculation.
Yeah, I do.
Okay, so the data certainly favors a high conductivity and seems to disfavor an amorphous. Okay, so I wanted to look some more about the structure of the crust that forms with the impurities. Some of the impurities have remained behind in the liquid, but you still have a bunch of impurities. And so actually to do this simulation, we froze the sample with a bunch of impurities. It looks really ugly to begin with. And then you anneal it. You heat it up. You run for a long time, in this case, a month and a half. And you slowly cool it down. And what we get is this very regular crystal. So you can see the impurities, and in particular the red are the oxygen, the lowest Z impurities. So even with lots of impurities, we form a regular crystal. So that's what the molecular dynamics is telling us, that impurities do not give you an amorphous solid. You can look in a little more detail as to exactly where the impurities sit. Maybe I'll come back to that. Let me just say a few words about the thermal conductivity. So the thermal conductivity, in this case, we're assuming it's carried by the electrons. The degenerate electrons have relatively long mean-free paths. So the thermal conductivity depends on the density of electrons. And then it's divided by a Coulomb logarithm that's describing the electron-ion scattering. And that Coulomb logarithm is an integral over the static structure factor. So a little bit of terminology. It's a density-density correlation function. So this is the charge density of the ions. So you're just summing over all the ions. This simulation had 27,000 ions, so you sum over the coordinates of each guy, and it's just that Fourier transform gives you the density. You calculate that at one particular time, and then you average over all times to get the static structure factor. If you had a pure system, no impurities, a one-component plasma, an ideal crystal lattice, at some temperature, you get the green static structure factor, and then there are spikes at the Bragg peaks. You have a crystal lattice of particular momentum transfers in the location of the Bragg peaks are these red dotted lines. And actually the crystal does have spikes. The spikes are near the Bragg peaks, but they actually happen at slightly lower Qs. So the unit cell is just a little bit bigger. In fact, there are 2.1 ions per unit cell rather than 2 for a normal BCC lattice. And so you have a few impurities, interstitial sites. They slip in between the lattice sites. And also you see that the black, it's a little bit noisy because of statistics, but it's significantly above what you'd get from the pure system. So you're seeing some effect from the impurity scattering. And in fact, that effect is a little bigger. If the impurities were just completely at random and uncorrelated, then the impurities would take you from the green up to the red, but in fact they go higher. So there are important correlations between the impurities, and so that enhances the scattering even more. And so the bigger the static structure factor, the bigger the Coulomb logarithm, and that reduces the thermal conductivity. So there's a little bit of a question. Brown and Cumming, just looking at the crust pooling, claim that they need an impurity parameter that's relatively small to explain the rapid cooling, and we've still got too many impurities remaining in this crust. And so the question is, what happens to the impurities? Do they get burned away from nuclear reactions, or is there some more chemical separation? You can also look at radial distribution functions. If you sit on one ion, what's the probability of finding another ion a distance r away? If you sit on a selenium ion, the probability of finding another selenium is this black curve. So this is the nearest neighbor. This peak over here is the next nearest neighbor, and so on. If you sit on an oxygen, as the probability of finding another selenium, you get a very different curve. And that just shows that the oxygen are sitting at interstitial. They're actually in between the lattice sites. And one thing you can use information like this to calculate is the rate of piconuclear reactions. You compress the system to very high densities, the zero-point motion eventually leads to fusion. For example, oxygen 24 is expected to burn near 10 to the 11 grams per cubic centimeter just from the zero-point motion. There's a gigantic screening enhancement factor. And so these piconuclear rates can be extraordinarily sensitive to exactly where the ions are in the cell. And so the fact that, come back all the way to here, you can see a bunch of oxygens that are kind of squeezed in between the other lattice sites, and so these oxygens can fuse at a relatively high rate. Okay, so the point of all this is the detailed molecular dynamics we hope to use to get much better piconuclear fusion rates in the future. Let me see. Nanoscale material science is big. This isn't as big, but let's talk about femtoscale. I want to say a little bit more about the pasta. The world is organized with short-range nuclear attraction, binds nucleons into nuclei, and then you have long-range Coulomb repulsion. Okay, so this organization explains, for example, why there are of order 120 chemical elements and not 1 or 10 to the 23rd, so on. At great densities near 10 to the 14 grams per cubic centimeter, competition between these leads to complex ground states, and that's the nuclear pasta. So this is a simulation in the nucleon coordinates rather than in the ion coordinates, which is what I was doing before. we've got a simple phenomenological model. It's just a short range, very short range repulsion, intermediate range attraction. The parameters are adjusted to reproduce the saturation density and binding energy of nuclear matter. And then you have Coulomb repulsion, the screen Coulomb interaction between the protons. Here's an example of the proton density in our simulation. This is about a third of nuclear density. This particular case had a proton fraction of 0.2, which is a little high for an isolated neutron star, maybe a little bit low for a proto-neutron star during a supernova. And you can get complex shapes. This is related to spaghetti, but in our case, the spaghetti tends to bend around and actually branch, and a little more complicated. But that may be a sensitive function of the interactions. You change the interaction slightly, you can get different shapes. You can ask for observables like the thermal conductivity or the shear viscosity. The shear viscosity, again, it's the momentum carried by the electrons. So the shear viscosity is some density of electrons divided by a Coulomb logarithm. In this case, it's electron-proton scattering. So we have a static structure factor. It's just the proton density, and we form the density-density correlation function from the simulation. And the black curve is S of Q as a function of momentum transfer Q for the protons. Okay? If you're interested in the neutrino opacity during supernova, the weak charge of a neutron is much bigger than that of a proton. So the neutrinos actually scatter from neutrons, while the electrons scatter from the protons. So the red curve is S of Q for the neutrons. So instead of summing over protons, we just sum over neutrons. And for example, at low Q, you can have neutron density fluctuations, but any proton density fluctuations at long wavelength get screened. So S of Q goes to 0 faster for the protons than for the neutrons. So at low Q, you see that difference. At intermediate Q, you're scattering coherently from the structures, from the pasta that's in the system, and so you get a big enhancement, a log scale. And you can think of the height of S of Q as the effective number of protons, for example, that you're scattering from. You have this pasta, and there's actually a limit. You can't, a given piece of pasta has lots of protons in it, but you can't scatter from all of them at once. If your wavelength is very long, then you can see the whole piece of pasta, but you actually see the other strands of pasta which is squeezed into the system, and the other strands tend to screen, the Coulomb interactions tend to screen the piece of pasta that you're trying to scatter from. So at low Q, S of Q is small because of ion screening. At high Q, S of Q is small because of the form factor. Pastas are big, and so you do elastic scattering from a big object at high momentum transfers, and you only see a tiny fraction of the object. And so there's some intermediate Q where you can scatter from as many as possible. Nevertheless, the finite size and the ion screening, because the pieces of pasta almost by definition are packed in really close together, this effective number of protons only rises to about 20 or so. And you can never get a situation, at least for our simulations, where you're scattering from thousands of protons. As a result, we find that the viscosity of the pasta is not greatly enhanced by the non-spherical shapes. You scatter from the pieces some effective number of protons, and it doesn't really matter tremendously what shape the pieces are. It just matters how many protons there are and how closely they're packed together. And you're actually scattering from density contrast. there's a lot more neutrons in the system than protons. But the effective number of neutrons, this peak S of Q for the neutrons, is actually smaller than that for the protons. And the reason is that the pasta sauce, all the neutrons outside the pieces of pasta, reduce the contrast. So the difference in neutron density outside compared to neutron density inside the pasta is not so great. So actually the density contrast is less for neutrons than it is for protons. And the reason is there are no protons outside, while there are neutrons outside. Okay, so bottom line, in contrast to conventional complex fluids, where if you have large non-spherical molecules, that can dramatically increase the viscosity. But here, we don't find any difference. Okay?
May I ask what is the critical thing about the nuclear pasta that's different from conventional complex fluids that makes this?
It's really the degenerate electrons.
Okay.
So the momentum, the viscosity is carried by the electrons, and the electrons don't care so much about the shapes of the pasta. But if you have a complex fluid, you have a complex molecule, and then it bumps into another complex molecule, and they can't move.
So, okay, so it's essentially in that case, it's just the size. You've got bigger things.
Yeah, that's right, and the shapes tend to bump into.
Quite intuitive then, which is kind of good. The difference between the two is
Nothing mysterious.
that's a shame.
And the flip side of this is actually good, and we don't really have to have a detailed understanding of the complex shapes, because then we'd be lost. Because to actually predict exactly which shape the pasta is.
So do you have an
really
idea,
hard.
but you say it's not greatly enhanced, but is it, is it some order roughly?
Yeah, I
What
mean,
that means?
let me say it this way. Here's a simple approximation. The viscosity depends on the density of electrons, and then Z star is just the height of the peak here. In this case, it's about 20. It's the effective number of protons that you're scattering from. And the peak has some width, so I'll call that delta Q. Oops. And so it's the area here, which is just Z star times delta Q. So if you have some idea of the effective number of protons, then that gives you roughly what the viscosity is. And actually, this effective number of protons can be smaller than the size of a nucleus at lower densities. So even though the pizza pasta is bigger, there's more interference from other pasta. Here's one probably very useless fact. The shear viscosity of pasta is 100 billion times more viscous than that of honey. And that's just the density of electrons. The stuff is really dense. Okay. I'll ask the moderator if I still have any time left. The last thing I wanted to talk about is the strength of the crust. So if you're interested in breaking the crust, for example, in a giant flare, how strong is it? And so what we're going to do is actually take a molecular dynamic simulation of a crystal and push on it until it breaks. So the breaking strain is important for giant flares, and also if you want to build mountains which could radiate gravitational waves, how big a mountain before the crystal collapses, we want to look at the strain. Okay, we're going to hear a bunch more on magnetars, very strong magnetic fields, neutron stars with very strong magnetic fields. Sometimes, very rarely, they give out these incredible giant flares, and all I wanted to say here, well, here's time, there's the flare, so for 0.2 of a second you get this incredibly bright X-ray and gamma ray burst saturated the detector in this case. 410 to the 46 ergs during that 0.2 of a second spike. So this huge number is luminosity of the sun. Well, the sun puts out that much energy in 300,000 years. And so one of the things you wanted to understand is how can a flare be that energetic? So what's the mechanism for a giant flare? Well, Thomson and Duncan proposed this crust breaking. You have a twisted, very strong magnetic field that diffuses and stresses the crust. At some point, the crust breaks, allowing the magnetic field to reconnect, and that releases the huge energy. So the huge energy is assumed to be associated with large energy stored in the magnetic field. And so with magnetar strength fields, there is enough energy, so that's the easy part. But if it's the crust that controls whether the magnetic field reconnects or not, the crust must be very strong in order to control the large energy in the B field. If the crust isn't strong, then the magnetic field will basically just ignore the crust. And then this mechanism wouldn't explain the triggering of the giant flare. Let's come back very quickly. Whoops. Yeah, here we go. So there's the flare. In the tail of the flare, you see the rotational period of the star, and then people have observed the quasi-periodic oscillations, which may be associated with shear modes in the neutron star crust. And the speed of those shear waves depends on the shear modulus. So we've calculated the shear modulus of neutron star crust. Basically, you just deform the molecular dynamic simulations a little bit and see how the energy rises. Actually, we're interested in the breaking strain. That's what we're really after. But to get the breaking strain, we have to basically do a really good job on the shear modulus. So our calculations are these little points here. The shear modulus goes like a typical Coulomb energy, Z squared over A is the distance between ions times the density of ions, and then there's a dimensionless coefficient, which is what we plot up here. And this is plotted versus 1 over temperature. The melting temperature is here, and then very cold system is off. So there. The older Ogata et al., these are Monte Carlo simulations of the shear modulus as opposed to molecular dynamics. Ogata et al. Ignored the electron screening, and we find that electron screening reduces the shear modulus by about 10%. We also find that the shear modulus is remarkably independent of impurities. You add a bunch of impurities to the system, you get almost the same shear modulus. Okay, a lump, gloriously called a mountain, on a neutron star. If you rotate it, that's a rotating time-dependent quadrupole moment. It radiates gravitational waves. LIGO is already remarkably sensitive to gravitational waves on a neutron star, and there are direct upper limits on the heights of mountains less than a centimeter. So I drew this scale picture of a neutron star mountain. 2 kilometers wide, and it's a few millimeters high. Okay, one assumption you could make is that an accreting neutron star is gaining angular momentum just from the angular momentum of the material that accretes onto the star. That would tend to spin up the star. And then if it's in spin balance, where the torque from gravitational wave radiation, which slows down the star, if that matches what you gain from accretion, then you can make a prediction for the expected amplitude of the gravitational wave radiation, and the faster the accretion, then the larger the gravitational wave radiation, the larger the gravitational wave amplitude, to balance that accretion torque. And so, with that assumption, you can make predictions just based on the observed accretion rates for some systems. But for this spin balance assumption to make any sense, a neutron star has to be able to support a big enough mountain, and so you need the crust to be strong enough to hold up that mountain against the big gravity. So what we do is just take a simulation volume and deform it. One example is where we use periodic boundary conditions, but we start with a cube and then we slowly deform the boundary conditions to stress the crystal. So what we can plot is the shear stress versus the shear strain. So the stress is the force that the crystal pushes back on the box. So if you try to deform the box, the crystal pushes back with some force per unit volume, and that's, or per unit area, excuse me, and that's the stress. The strain is just the fractional deformation. You start with a cube and deform it by 10%, that would be a strain of 0.1, and so on. And what you get, originally it starts linearly, and that's just Hooke's law. That the stress versus strain, the slope is actually the shear modulus. But you can keep deforming the system, increase the strain, until finally the system breaks. And the simulations are for different shear rates. If you deform the system really quickly, then the system doesn't have enough time to break, and it gets to bigger deformations before it finally fails. If you deform it more slowly, it has time to break earlier, and then finally for very slow deformations, we find that it tends to converge, and you get a remarkably simple curve. Straight line, and then just an incredibly abrupt, catastrophic failure.
Can I ask a slightly different question? So the stress-strain relationship would be truly linear if this was Hookean. So
If this was,
a Hookean system.
yes.
So essentially, so I guess that's not exactly linear.
Yes.
So that's an estimate of how close to Hookean, in some sense, this system is.
Yes.
And because when we model these things, the elastic systems for the oscillations and all that stuff, the standard assumption is that it is.
So the oscillations are very small.
But I'm just talking about the generalities. It is assumed, right, typically, that it is a Hookean system. And this basically says that it is.
No, this looks very Hookean to me.
It's
difficult to see from the screen.
No, I'm just thinking about the fact that you can always quantify it, right?
This is a very small system, and I use such a small system because there are some very slow strain rates, so they ran it for a really long time. So actually, most of that curvature is a finite size effect.
Okay.
And if I used a bigger system, it actually is straight. I mean, it's a remarkable result. I didn't expect it. That the system basically is linear, and then it fails catastrophic.
As it's telling you that the crystal is brittle.
Crystal is
Crack like a rock, not deform like an iron.
yes. It's not. Plastic flow is not what's going on.
Are there any impurities in this?
Not in this simulation, but I have done simulations with impurities. Impurities somewhat weaken it, but not very much.
But you still have the catastrophic behavior.
That's right.
So what's the temperature here is completely exactly zero, or
Oh, the temperature?
can you play with the temperature in this experiment?
Yes.
So
If you increase the temperature, it gets a little weaker. So I didn't show it, but it breaks a little bit earlier. This
Still remains the same order of magnitude. The same order of magnitude.
yes, this particular simulation is at a temperature that's about 10% of the melting temperature. The closer you go to the melting temperature, the weaker it gets.
Okay.
And that may actually be relevant. If you have a flare, or a giant flare, it breaks, it heats the system, that may cause other parts of the system to fail more easily.
So is it temperature constant simulation? Or
Yes. Oh,
So you.
whoops, I spoke too quickly. We've actually done it both ways. Constant energy or constant temperature. Very similar. Just a couple quick movies. How does it fail? A normal solid like silicon actually fractures. You open a void, there's a crack that propagates, and you break the top off. This system is under very high pressure. The pressure prevents the formation of voids. So the crust does not fracture. It fails catastrophically, but it's not a fracture. So actually, I'm going to show you a movie. We have a frozen layer of ions along the top, which is moved to one side, and that stresses the system. We actually put a defect. We drill a hole in the middle, if you can see that little point there. And so you might expect the system to start breaking from that hole. And the red is the local deformation away from a simple BCC lattice. Let's try that again. The pressure holds the system together, so it can't just break off from that point. And finally, to get the system to fail, you just have to bodily deform lots of the system. So the system is very strong. Whoops, let's try this way. What about, for example, grain boundaries? You could have microcrystals in the crust. So this is an example of a simulation. There are actually 8 grains with different orientations that were chosen at random. The total simulation volume has 12 odd million ions. So there's about 1.5 million ions in each grain. So that's what these little regions. We're going to first anneal the system to try to improve the fit along the boundaries just a little bit. And then there's a frozen layer at the top that we move to stress the system. So you're just annealing it, and now you're stressing the system. You see that it starts to break along the boundaries as you might expect, but the pressure holds it all together, and to get it to deform, you really have to bodily deform lots of the system. So the take-home message from all that is neutron star crust is very strong. It's strong for 2 reasons. The great pressure suppresses the formation of dislocations, voids, and fractures. So that inhibits many failure mechanisms. At the same time, you have long-range Coulomb interactions. Each ion is interacting with thousands of its neighbors. The system is still strong even if several of those redundant bonds are broken. So if you have some local defects or something like that, break some of the bonds, you still have lots more interactions which hold the system on. So the long-range Coulomb interaction and the high pressure leads to a very strong system. We find neutron star crust is the strongest material known. It's 10 billion times stronger than steel. So that's the breaking stress, the force per unit area that you have to put on crust to actually break it. The breaking strain, so the fractional deformation at failure, is very large, around 10%. Even when you include the effects of impurities, defects, and grain boundaries. So, strong crust can support big mountains. That's very exciting. So we strongly encourage ongoing and future searches for continuous gravitational waves from rotating neutron stars. Large enough mountains could definitely be out there. Okay, maybe the thing to end up with is what field am I working in? Is this crust breaking calculation, is it nuclear physics? Well, yes, I actually am a nuclear theorist. And the nuclear reactions determine the composition, the heating, etc. We certainly are interested in astrophysics. You could ask the role of a strong B field. I've ignored the drip neutrons. So that's something you could think about. The fact that the neutrons are superfluid, does that matter for the breaking strain? Is this material science? Neutron star crust is uniquely strong because of the high pressure and long range interactions. Can you think of something else maybe that you can make in the laboratory with long range interactions under pressure? Maybe that's patentable. We had a little discussion yesterday about earthquakes. Maybe this is planetary science. The high pressure in the crust suggests that there could be an analogy with crust breaking with deep earthquakes. So earthquakes very deep down in the earth occurring at pressures where you don't expect rocks to be brittle. You instead expect them to flow. Nevertheless, you do get deep earthquakes, which are observed to happen. Okay, and emphasize collaborators. In particular, Kai Cadell is a material scientist at Los Alamos that was crucial for the breaking strain calculations. Some of the graduate students involved, Lillian Caballero has now graduated, and also Joe Hutto is working on the shear modules. Okay, so thanks very much.
You mentioned surface cost in the past phase. What about electrical conductivity?
So the electrical conductivity follows exactly the same story as the discussion.
So it's similar to the BCC stuff. Not even factor 10 different. I'm asking because it could affect things like the magnetic field evolution in the crust.
Yes, so nothing drastic happens to the electrical conductivity when you go from nuclei to plasma. An interesting question is if the crust were amorphous, what would that do to the electrical conductivity? Is a magnetar crazy with an amorphous crust? Would the electrical conductivity be so low that Joule heating, whatever, system would explode? But I don't think there's nothing dramatic going on with the pasta for the electrical conductivity. I'm sorry.
To push this deep earthquake analogy a little bit further, so a lot of the deep earthquakes that we know happen in zones where you have essentially bits of the crust pushing down into the mantle, so you're carrying colder bits down. Now, is there any possibility whatsoever of having that kind of stratification process going on in a neutron star? Or is it simply too difficult to get radial motion of crust size? To think all the mechanisms that are proposed, the phase transitions, the shearing, dehydration instabilities are all because you're pushing essentially portions of the crust down under other portions.
You're asking where the fault lines are.
Yeah. Can you get, essentially, could you get radial motion of that kind if you're going to do neutron-star tectonics?
Yeah, you want inhomogeneities somewhere.
Yeah.
I was going to write some questions, so let me. So clearly, how,
Without Benioff zone on a
where,
neutron-star.
Why?
who,
I like the curse breaking mechanism.
The amount of cross break.
You can have, so this is somehow presumably related to giant flares. And then the question we were talking about yesterday is how are flares related to giant flares? So you have big crust breaking, which gives giant flares, and little crust breaking giving littler flares. You observe lots of little flares. Or are small flares not related to crust breaking?
Or even though there are two types of small flare, which is what the data seem to suggest. One that might be crust breaking and one that might not be, which is even worse.
Or better. Richard.
Yeah.
Yeah, it wasn't completely clear to me. Did you see at the moment when the cross breaks, plates shifting with respect to each other? So, if you include magnetic fields, I guess that would be difficult.
Yes and no. Some effects of magnetic fields are easy to include. One of the things the magnetic field does is it could quantize the electrons and change the electron screening length. And so you can get an electron screening length which is different along the field or against it. But actually the simulations are not greatly sensitive to this screening length lambda.
Okay, but I mean if there's some kind of magnetic field frozen in the crust, then magnetic tension would try everything to prevent that, from slipping. If you have magnetic field lines crossing.
Depends on the configuration. I mean, if you've got twisted fields, then in Duncan's picture, it's the diffusion of the twisted field that wants to make the crust break. So the crust is trying to accommodate the field, which is pushing it to move.
So locally, I don't know if this helps, but locally one could imagine breaking along the field lines so that, you're not, this prohibited from the magnetic field as long as you break in the right direction.
Right.
So the weird thing about that, if you did that, you would expect to see the flares at the same rotational phase, probably, because you'd expect them to be tied to a certain location on the field, which we see in half the sources, but not in the other half,
But you don't know,
which is great.
you don't know the determinant of the field.
No, you have to infer it from the pulsation shape, which,
Yeah, so
Could be very irregular.
yeah.
So it's kind of a question of length scales, like these
Yeah.
length scales he's talking about here, maybe thousands of Faraday. The magnetic field configuration.
I think that was a question I was gonna say. So, do we have any idea how to scale up from the kind of simulations you do, and when it breaks in this very, very small scale, how we scale that up to give us some idea of some, let's call it the hydro scale, the kind of thing that actually we're modeling when we're thinking about how the flares work. We look at the, because that's the level where if you wanted to model a fracture,
Yeah.
that they would be on the hydro scale, and this is all information that has to go in somehow. But we need to bridge that gap, and that's obviously not easy, right? But do we have any ideas how we do this?
I mean, one question you ask, in an earthquake, you have a rupture zone. The crust fails at some point, and it ruptures along a fault for some distance. What's the analog of the fault? How big a region? What's the geometry of the crust that fails? Those may be more macroscopic quantities. They're not the microphysics. I think the microphysics is this breaking strain.
Yes. If I think about a frozen lake,
Uh-huh.
and it's got the ice on the top and the water below, the density of the ice is the same, but in a neutron star it changes by a factor of 10,000. What does that, how can I think analogously to ice on water, or does that 10,000 change drastically?
Yeah, so neutron stars are like ice and water where they are, and they're unlike when they aren't. You have a solid crust over a liquid interior. So that's like ice over a liquid lake. But then you have a liquid ocean on top of a solid crust.
So the sun is shining. So they're like that.
Okay.
No, but right, but I'm thinking like, suppose a bit of it breaks, you know.
Yeah. So let me.
There's this 10,000.
Yeah, your factor of 10,000 is important. Earthquakes tend to happen where the crust is strongest. So you have a fault, and the fault is held up at the strongest point. And so when the crust breaks at the strongest point, then the fault can move. So we're interested where the crust in a neutron star is strongest. And that's probably the base of the inner crust near the boundary with the pasta. So you want the system to be as dense as possible, but not possible.
It seems to me that if we neglect magnetic stresses, that it'd be easiest to shear along equipotentials, gravitational equipotentials.
Yes, it's certainly easier to move.
So back to Anna's point about, can you get a subduction zone?
Yeah.
Maybe it's very hard because of
That's
this
what I was
huge
thinking.
density.
But accretion has to build up in layers. So if some latitude, for some reason of the star, the low-Z material went there, then you'd have a column of low-Z material, which would have a vertical boundary with the high-Z material. So it's not impossible to think of.
Now, in terrestrial solids, if you put matter under pressure in excess of the shear modulus, it becomes ductile. And why is that not happening here? Is it a question of screening links?
I think the long-range interactions are really important. And I mean, if you have short-range interactions, it's only a few lattice planes. And when you've got enough pressure to slip by the force from a few lattice planes, you just do that. Here, you're interacting with many lattice planes, so it's much harder to slide one piece by the other.
You said that the pressure prevents the existence of dislocations. Why is that?
You can't open up voids.
Right, but you can put in joining lattice layers, for example.
It tends to suppress or the if you have grain boundaries, those grain boundaries are pushed together really hard because of the high pressure. So the grain boundaries aren't as weak as you might have thought. The two microcrystals are always in very, very good contact because of the high pressure.
So it's an extraordinary case in physics where boundary conditions almost don't matter. Is that you're putting together these different layers, but it's really, the strength is determined by the bulk properties, not by funny little geometrical structures you put in.
Yeah, and I think the long-range interactions say that the local defects are not as important as you might have thought, because you're averaging over bigger regions.
So if you could tune down your lengths, your screening lengths,
yes,
something short, those boundaries would matter a lot.
Yes.
Yeah.
And my collaborator Kai really wanted to do that because it's a lot faster computer time. It took me a long time to get him to actually run with realistic.
Well, that's why you need 12.8 million points, right? Is because of the long lengths.
The computer time to do 12.8 million ions, where each ion interacts with 5,000 of its neighbors, is a lot more than if they were only interacting with 50 of its neighbors. So these simulations are about 100 times more computer time for a given number of particles than a conventional short range condensed matter system.
Can you say something about the energetics of this strain process? I mean, you build up, you put some amount of energy in the Dickian phase of the process. So what happens to this energy beyond the yielding point? I mean, how much do you lose? How much remains?
So the total elastic energy that one can store in the crust, a breaking strain of 0.01 or a breaking strain of 0.1, it goes with the square of the breaking strain. So this is 100 times more energy one can store with the higher breaking strain. Even so, that energy is probably not quite high enough to melt the crust. But if you add a bunch of magnetic field energy, then you could melt the crust. And so one important question is, when the crust breaks, does it melt? Does the magnetic energy cause a large part of the crust to actually melt?
So what fraction of the initial energy remains as elastic energy after the crust breaks?
And certainly it could go into oscillation mode. The gravitational wave folks want somehow the crust breaking to excite F modes in the crust to get big time-dependent quadrupole modes.
They want the same for everything in the sense. They want to excite the F mode no matter what. They want the F mode.
I want the superfood.
Well, there I think the reality is that that's never going to happen, because the F mode is a global, mode with 10 kilometer scale wavelength. So that's never ever going to happen unless you've got a catastrophic event when not just the crust but the entire system just reacts. So that's why these searches for the same things, gravitational wave searches for the torsional modes in the crust are completely pointless, because those modes don't radiate gravitationally at all. So it is true, from the gravitational wave point of view, you want essentially communication with a high density region. That's the key point. So the question is, with all these mechanisms, are they global enough that you can excite core dynamics? That's the big question for gravitational waves. And obviously that relies on how does the crust break, if it breaks, and is this flare coupled? And I think the magnetic field is important. Does it couple to what happens in the core?
But 4 times 10 to the 46 ergs is a lot of energy, right? Can you really get that much energy without invoking a large part of the crust?
Yes, if the field is strong enough.
If it's strong enough,
you can easily do it.
I think it's all got to do with how localized these things are. If you go to localized events, there's a high multiple events, then the gravitational waves emission is irrelevant. It's going to be very small.
Yeah.
So I mean that's why, you know, okay, so as a gravitational wave person, occasionally, you know, you would like this to happen, but some of these events I think is incredibly unlikely. You should search for the signals, of course, but it's difficult to see how you would, you know, I like the F mode too, but I don't think it's got much to do with it. It's kind of problem.
I thought you like things in the other part of the alphabet, starting like with R.
W. No, but
We'd
it's
like
not
to have a little bit more detailed picture of the geometry of how this breaks. I mean, it's unlikely to excite the F modes, but where does it break? How big a region? Which direction does it break?
Well, certainly, you know, the geometry will have something to do with. Suppose for a moment that the QPOs that you see from the flare events have got something to do with the shear modes in the cross. Just take that as an assumption. Then, if that is true, then the geometry of the breaking will tell you something about what multipole modes are excited. So one would like to be able to invert in the ideal world whatever the mode spectrum is to say what kind of geometry comes from the fault or the mechanism. And then in principle, I don't see why it shouldn't be possible in theory. In practice, of course, the problem is much harder. So sure.
Yeah, and you also have the problem that not only do you excite the mode, but you have to communicate it out to where you can observe it.
It's extremely possible that there are things happening that we don't see, because we just don't see it modulating the X-ray emission. Or it's happening at higher energies, which...
Higher frequencies?
Higher photon energy, because the amplitudes tend to go up. So on the flare that we got RESI data for, we got a proper look at the higher energies. And the amplitudes are much higher up there and the QPOs are much sharper. But they're much less quasi, than they're practically periodic. So, but we only got that. MNXT doesn't go to high enough energies to let us do that. The Hexd bit that's on there is not good enough resolution to tell anything. So again, if we get one with Fermi, we'd be able to look at that properly. But that relies on the universe being kind.
So that's another question I'm going to put up is when is the next flare?
Wait, is the next flare? It's not something we can work on this week.
It's like asking when California is going to slide into the Pacific.
Might occur this. What sort of value were you getting for the shear modulus? I didn't notice.
Oh, there's. Let's go back and see. Whoops. Oh, I'm sorry. The wrong way. So the shear modulus scales with density. Basically, that's the biggest factor. And this is very conventional numbers. So it's largest near the base of the inner crust, just when the pasta is going to start to form. It depends some on the Z's composition of the ions. So you can get factors of a few. And also the ion density, so the fraction of the matter that's not in neutrons. Are you going to say a little bit about how the shear modulus depends on composition?
I wasn't going to, because Niels asked me to just talk about the observations.
Did I?
Yes, I did.
But you've just been asked to do something else.
But basically it goes like this. So that's...
But my
rises, as you come in through the neutron star, it rises to about neutron drift and then it dips down again and then comes back up. Then it's dominated by the base of the crust.
But that number near the base of the crust is 10 to the 33 or something? The shear modulus, isn't it typically? I can't remember the number.
Shear speed is about 10 to the 8 centimeters per
No. You're talking about the shear modulus itself.
Yeah, shear modulus is an energy density.
I mean, it's conventional number, so.
Yeah, which is, I'm trying to remember, isn't it about 10 to the 33? Anyway, the point, the point I'm driving at is if you take that and multiply by the volume of a unit cell, and you imagine you're stressing things near your critical strain angle, I think the typical energy densities in the strain field, which will be supported by the electrons, is going to be MeV type energies, I think. So my question is, if you have these points in your simulations, is it possible that we just start deforming the nuclei through a continuous sequence of shapes and have a failure mode that way?
That's a good point, is that I did simulations in the ion coordinates where you ignore the internal structure.
Yeah.
And when you shear the system, you generate really strong electric fields inside. And so they will deform the nuclei. And so the polarizability, for example, of nuclei matter. And that's been neglected. So as you approach the pasta densities, the internal structure and the excitation of the nuclei is probably relevant. And if I had to guess, it will reduce the shear modulus in that instead of just having the point charges deformed and giving you this very strong magnetic field, electric field, the nuclei will deform to try to cancel some of the electric field. So that the internal structure will reduce the shear modulus.
Well, I'm wondering if you would lose the catastrophic failure entirely. You just deform through shapes, and maybe it even occurs at somewhat lower densities.
I mean, so exactly where the crust is strongest could very well depend on things like this. If you go to low enough density, then the nuclei are well separated, and so their internal structure doesn't matter.
Right.
But then it's weaker because the density is lower.
Yes.
So there's some trade-off. It's near the density where the pasta formed, but exactly how much above is an interesting question.
In CGS units, this helps about 10 to the 29 or 10 to the 30 is probably closer to the shear modulus.
That's ergs per cubic centimeter?
Whatever CGS.
That's whatever the CGS is.
We'll let you work that. Should we?
Grams per centimeter per second squared.
Time to move on, do you think?
Maybe we should
Yeah, sorry.
continue this discussion.
Yeah, I just blame the moderator.
Yeah, you move right.
Can I ask a question?
Sure.
So maybe I missed you have already told, but do you have some estimate of the size of the grain? It would be very depend on the profile, cooling profile.
Yeah, my prejudice is the grains are not going to be very small. We've done simulations with very small grains, and we can watch them in yield, and the grain size grows. So my prejudice is the grains are much bigger than we can actually simulate. But how big the grains are, I don't know. There's really subtle physics as to how the grains form.
So the breaking index would be
our simulations get stronger the bigger the grain size. So even with these small grains, the strength is reduced some, but not all that much. So with big grains, they're probably even stronger.
Shall we perhaps have coffee?
Let's take a 5-minute break and set up the next talk.
Yes, I guess.
It's about 10 to the 30, of all the 10 to the HO speed. 10 to the 14 density of those, right?
Yeah, 10 to the 14, I think. Yeah.
It is order 10 to the 30.
So then if you consider a unit cell that's say 10 fermi on the side, high density, that's then the minus 12 centimeters, that's high. And then the minus 26, if we multiply it
You have to be
times
careful. The system has to be
you get
much bigger
the minus 3.
than that screening line. And it's actually like
29
10
minus
or something.
26.
So you need, and so these 26